So I've spent a little bit of time thinking about this problem, and I've looked at it a couple different ways, and I keep coming back to using a system of equations to solve this. So as I set this up, hopefully it makes a little bit of sense, and you can follow along and see um, basically my approach and how I perceive this problem. But if there's another method that you've got that would help solve this, I'm more than willing to listen to that and see it. Perhaps it's my math teacher brain that's working here, but I always come back to a systems of equations to solve this. So anyway, in this linear momentum example, we have a shuffleboard. So we have an orange disk and a green disk, where the green disk was stationary and the orange disk is going to strike it. After the collision, since this is a glancing blow, we're shown that the orange disk careens off at 37 degrees and the green one shoots off at 53 degrees. And so our job is to try to figure out what the final velocity of the orange disk and the green disk is after the collision. So we're told along the way that the mass of orange is equal to the mass of green. So we'll see pretty quickly that the mass actually doesn't come into play in the computations here, where mass is normally a critical component of momentum. If they all have the same mass, then the mass component essentially factors out of the equation. But I also want to remind you before we get too far, if I'm worried about the final velocity of this orange puck or disc or curling stone, we could always decompose that into its x component and its y component. And this is where the system of equations is going to come into play. So the combination of the x and the y, the horizontal and vertical component, is what makes this velocity final for that orange disk. And then similarly, for the green disk, the final velocity of it would be its combination of its x and y component vectors. So if we separate the math into a row of x components and a row of y components, then I think we ought to be able to establish a system of equations that our calculator can solve for us, or we could solve by hand. So this is where, the component of vectors is really particularly helpful. While a vector requires a description of an angle and a magnitude, or a direction and a magnitude to that numerical quantity. If we decompose into our horizontal and vertical components, then we can combine all of our horizontal components together and do our own work with them, separate from the vertical components. So I'm just going to take a minute and set up what we know, and then I'll get into the equations. So I would encourage you to do the same, identify what we know, and then report those in a given column. So this is what I'm reporting and how I'm reporting it. First off, so that I can avoid a little bit of confusion, I'm going to avoid the letter O and the letter G for orange and green. And instead, I'm just going to call these objects 1 and object 2. To me, that makes a little bit more sense. Now, my labeling here, hopefully you can follow along too, is that I'm indicating that the velocity of object 1 in the initial position, so before the collision, in the x direction, so velocity object 1 initial in the x direction, was 5 meters per second, and so on. So we have the velocity 1, velocity 2, initial and final, all in the x direction. These are all of our horizontal components grouped together. Also, I'll note that to get the final speed, again, I'm just considering the right triangle that exists over here. If we have a right triangle drawn with our horizontal and vertical components, the x coordinate is the adjacent side to the 37-degree angle. So if we knew what the final velocity of object number 1 was in this diagonal direction, if we knew the length or the magnitude of that vector, we could simply multiply that length times cosine of 37. This hypotenuse length of the triangle would allow us to find the adjacent length of the triangle, and so on. So I'm using 37 degrees for the orange puck or shuffleboard piece, and I'm using 307 for the green one, because if we used 53, then your understanding of the unit circle ought to clarify that here. Our sine and cosine components may disagree since this is pointing downward. Specifically, our sine component would. So as I had mentioned throughout this class, I prefer using the quantity relative to the unit circle angle. So that's why I'm calling that one 307. I think it would work out just fine if you called that negative 53 degrees as well. Then finally, I'm noting that mass 1 is equal to mass 2, so those two objects have the same mass. And when I write the formula, I'm just going to use m for that. Okay, so according to our conservation of linear momentum, the law of conservation of linear momentum, we know that the momentum before the collision of the system must be equal to the momentum after the collision within the system. And the system that we're describing here is the collection of two pucks or two disks. So because this is true, we can also state that the momentum in the x direction is equal to the momentum in the x direction at the beginning and end of the event, and similarly in the y direction as well. So momentum initial in the y direction will be equal to the momentum initial final in the y direction. So that's an assumption that we're working on, which is true if we were to decompose this down to its components. So then what that also means is that, well, momentum is mass times velocity. And I'm going to say mass times velocity in the initial position plus mass times velocity in our initial position. Notice I'm using just the letter m here because m1 and m2 are the same. I don't need the subscripts. And then mass times velocity 1 in the final position plus mass times velocity 2 in the final position. Now I'm saying position, I should say final time, or at the end of the event. Then mass times velocity 1, and I should be clarifying this, in the y direction. So this was 1 in the x direction, and these were all in the x direction up here, so I need to be clear. Mass times velocity 1 in the y direction, initial, and so on. So mass times velocity 2 in the y direction, initial, and we'll continue. Keeping track of all of these subscripts can be a little bit challenging, but hopefully we've got it correct here. And a quick check can verify that. So 1x, 2x, 1y, 2y, and all of these are initial quantities. 1x, 2x, 1y, 2y, all of these are final quantities. Okay, very good. I think we're in good shape. Now, the reason why I said the mass, since both of these are equivalent, is irrelevant in this equation. Think about the math that we could potentially do at this point. It would be a little bit crude to do it right now, but it does show fact being true. If I wanted to factor out an m from this side of the equation, I could divide m from both of these terms and effectively move it to the right side. But in order to keep the equation balanced, I also have to divide the right side by m, and similarly with these quantities as well. But if I'm dividing m on one side of the equation to make this set of quantities disappear, then when I divide it on the right side to keep the equation balanced, they also disappear. So in this case, the mass quantities end up disappearing altogether from this problem. So the momentum, while it does require a mass component to compute momentum correctly, to solve for this velocity, component, we actually don't need the mass values at all. So now I'm almost ready to set up the system that I'm going to solve. So I'm just going to note here that V1 initial in the x direction plus V2 initial in the x direction. Now those are numerical quantities that we know from our given data over here. So that's going to be substituted with numbers in a minute. will be equal to V1 final velocity, so the diagonal velocity times cosine of 37, and V2 final velocity down the diagonal times cosine of 307. And then in our second row, virtually the same thing. Initial velocity in the y direction plus initial velocity for object 2 in the y direction would be equal to our final velocity down the diagonal of object 1 in the y direction. So we're accomplishing the y direction with the sine of 37, just like we were accomplishing the x direction with the cosine of 37 if we knew the diagonal quantities. Which, since we don't know the diagonal quantities, obviously we're going to solve for that. That's going to be an unknown variable. And then V2 in our final direction times sine of 307. Again, this is going to allow us to solve for this unknown quantity. Now, I don't know if it's going to help or not, but when we go to substitute numbers in the next step here, it might be helpful to consider just a single letter variable. So if I use the letter A to represent my V1 final and the letter B to represent my V2 final, maybe that'll help you see the setup a little bit more clearly. So I think I will show that in this next step. So let me get this cleaned up just a little bit. And I'm just going to make a side note. I'm going to say that V1 final is going to be represented by the letter A, and that V2 final is going to be represented by the letter B. Okay, so we now have, in this case, 5 plus 0 equals A cosine 307 or 37 plus B cosine 307, and then 0 plus 0 is A sine 37 plus B sine 307. Now, hopefully at this point, you're starting to see how this procedure is remarkably similar to some of the work that we were doing in Unit 1, how we were isolating variables and solving for resultant vectors. We'll just go ahead and set this up and then use our calculator to solve it. But one thing that we have to recall is that if we are going to use our calculator and the matrix menus inside it, we do want our solutions on the right side of this expression. So I'm going to do that now. And we'll just go ahead and report that A cosine 37 plus B cosine 307 is equal to 5, and A sine 37 plus B sine 307 would be equal to 0. And since A is our unknown variable and B is our unknown variable, then we can actually solve this with a matrix. So we'll set up the reduced row echelon form command against a matrix that has 2 rows and 3 columns, and we'll just require cosine of 307 or 37. We'll require cosine of 307 and 5, along with sine 37, sine 307, and 0. And this expression should return to us, if it's solvable, a matrix in the reduced row echelon form where the A quantity and the B quantity ends up being reported on the right-hand column. And again, we get that because the column A and B, left column, right column, ends up rotating to first row, second row, so top row, bottom row. So that's how our matrix system will work. And if we bring up our calculator here and create a new calculator page, we can jump into menu, choose option 7, then number 5 to call our RREF command, then menu 711 to create a matrix. we do want 2 rows and 3 columns, and we're using, one more time, cosine. Oops, let me just punch this in because my screen is acting a little bit wild. Okay, so I think we have that in there, and a quick double check, make sure we've got everything set up the way we expected it to. So cosines across the top, sines across the bottom, 5 and 0. This looks pretty good. I do want to switch my calculator back to degrees though, because I'm supplying degrees inside my trig functions, and I do want the decimal results, so I'll press Control Enter here. Okay, so with Control Enter, we do see the reduced row echelon form as a result. So that implies that A is equal to 3.9932 and B is equal to 3.0091. So we'll note that A, which we said was our velocity 1 final, that's our diagonal velocity, 3.9932, and B is our velocity 2 final, and that's 3.0091. Now, of course, we do need to pay attention to our significant figures, and it looks like I've got 3. It looks like all of these have 3 sig figs, so I think a better answer would be 3.93 or 993 and 3.009. Since we did rely on the calculator to compute our result for us, performing our dimensional analysis can be a little bit more challenging. But I think it's worth noting that before we started substituting any numbers in place, we ended up with an equation that contains only velocities as part of our function. This cosine and sine computation ended up being just a ratio. So the results from a trig evaluation is a ratio. So in all cases, velocities are the only unit that's being used. So rather than show our traditional dimensional analysis where we do the math with all of our units, I think just a note off to the side would be perfect. This tells me that you were thinking about the dimensional analysis and you did spend some time verifying that it would work. I went ahead and made this comment here. To say that the meters per second is the only unit that's used throughout the problem, I think that's okay. But to take it just a little bit further and make sure that we all clearly understand why that works, is that our calculator is performing the reduced row echelon form command, and it does that by applying row operations to the matrix. And if you recall with row operations, when we were studying that in college algebra, that only addition and subtraction of rows and scalar multiplication is permitted to modify those rows. So if we're only adding and subtracting, then we have to stay within our meters per second unit. And if we're multiplying by scalar quantities, numerical quantities, then we also have to stay within our meter per second unit. So I go on to explain that that's the reason why I know that the meter per second unit at the end here is completely correct. So I know that was a bit of a lengthy video to describe this, but hopefully the description makes some sense. I trust that the math itself works out just fine for you too, but it is helpful and pretty important to recognize that the components here are what allowed us to split this apart into a system of equations. And again, in my mind, the system of equations just became the obvious method after we set up the problem. If you've got further questions, please let me know. Otherwise, thanks for watching.